start the recording now. Okay, so jumping right into it, and we're continuing from where we left off on the introductory lecture. So in terms of what we do, the whole idea about signals and systems, and in fact, many of the things that you do in electrical engineering are really about finding models of the real world system and analyzing the model to see how the system should behave when you really put the thing together. And if you think about it, if you have to make something, before you put together the components and all of the wiring and spend money and so on, and then you actually assemble it only to find out that it doesn't actually work, then you have to go back to the drawing board. I mean, that's a very expensive and time-consuming sort of process. So what is usually done in engineering, and especially in electrical engineering, is that we try to model what the real-world system is doing. And if the model, first off, we have to get a good enough model, which is part of the challenge. And then if the model is good enough, then we subject the models to certain inputs and see what it does. What are the outputs from the model? Are the outputs doing what we want them to do? If not, then we have to decide if the model is at fault or if there's something about the way that the system was designed in the first place. So then you go back to the model and you tweak it, and then you send the inputs in again. And after you are satisfied with what the model of the system is doing, which is a representation for the system, then take that model and translate it into electronic components and into motors and into mechanical components and everything else. And then once a model is now in a real world prototype, then you test the real world, whatever it is, with the same signals that you tested before, and you look at the behavior. Hopefully, if the model was well done, the real world system shouldn't behave too vastly different from what the model was showing you from before. Okay? So our broad model is that for us is that whatever that thing is, the system, this system here, whatever that is supposed to be a fairly good shorthand representation of what the real thing is supposed to be. We send in some inputs and we get some outputs coming out. So we are going to formally describe some of these components as we go forward. All right, and every so often I'll stop to ask if you all have questions and the like. So the input signals. Normally the input signals are a voltage, a current, a force, a pressure, something supplied to the system. In electrical and computer engineering, whatever it is normally gets translated into some electrical parameter. So voltage and current usually, all right? Occasionally you could get resistance and capacitance. For instance, if you're using a touch screen computer in front of you right now, that is a capacitance input. If you touch the screen, it's capacitance that it's responding to. There are certain types of inputs that respond to resistance. So that type of signal, whatever it is, eventually gets converted to some electrical signal and we put it into the system. The output, of course, is something that we want, which is in response to that input. So we put in a voltage and we get something coming out, right? It may be another voltage, it may be a current, it may be a motor turning in a particular direction, right? That is the output. And then the system itself is what is taking the input and giving the output. But inside the system, there are internal signals as well, because the system, as you can imagine, will have a number of components of its own, and they have to send information from one component to the other. So there are little signals that go inside as well. And the signals are functions that carry information. So, for example, electrical signals, the information that will be carrying will be the voltage level or the current magnitude in a circuit. An acoustic signal, for instance, in audio or speech, right? It could be analog or it could be digital, and we'll talk about that in a second. Acoustic signals are air pressure variations, but you're speaking to a microphone and it converts those air pressure variations into an electrical signal. Video signals, the image that you're watching on the screen right now in front of you, are brightness variations. So as things change, it gets bright or dim, and that's how you interpret it as light and dark. And then there's color information in there as well. And then you have biological signals, which are the sequences of bases in, for instance, a gene. And we mentioned that last time, the coronavirus and the kind of signal that was sending. Right? So signals now are usually functions of one or more independent variable. And you would remember that from way back when you were doing your art maths and so on, dependent and independent variables. So for instance, the signal may be a function of time, right? Voltage and the currents that we deal with usually are functions of time. It may be a function of distance. So for instance, an audio signal, as it travels through space, as it goes from the source away from the source, it decreases at a particular rate. It is a function of distance, among other things. It may be something, maybe a function of force. So certain types of devices, depending on the variation of force on the device, produces an output. And of course, the DNA, I mentioned that again, the DNA base sequence, what makes up DNA, that particular sequence is a signal, and it is what makes a heart cell different from a liver cell, and it what makes each of us different from each other. For our purposes, electrical signals are usually a function of time. Yeah. And our particular course here, we are looking, signals and systems tries to help us with determining the behavior of the signal characteristics and the signal performance, and the system performance, sorry. So in terms of the signal waveform, we look, among the things that we like to see is how it varies with time. And variation with time is what we call frequency. And we're going to look at that, and we're going to see it vary in time just by examining the time signature. But also to get another look at it, we're going to do something later on called the Fourier series and Fourier analysis, which allows us to see how the signal varies with frequency. So you're actually getting a different look at it. And then we also look at things like the system performance, gain, which is something that you would have met before. When you're talking about like a small signal amplifier, you put a small voltage in and you get a much larger voltage coming out. The ratio of the output voltage amplitude to the input voltage amplitude gives you something called a gain. So many systems have a gain function. The output is bigger than the input in magnitude. So that is one of the things you want to see. And then, of course, another important thing is how does that gain, for instance, vary with frequency? For instance, your hearing. Many of us, your hearing is not a constant, it's not a nice level behavior. So for instance, low frequencies, you hear in one way, and very high frequencies, you hear in a much different way. And depending on your age, at your age, what you would hear at high frequencies, for instance, I may no longer be able to decipher. Right, so that sort of thing is something that a system model will help you to figure out. So if you're designing the electronics, for instance, for a type of hearing aid, you need to know how a person's how the ear system and the hearing system for a human, how it works. So you model that in some form or fashion, and so that when you are finished with a model, if the model behaves how you want it to behave and it mimics the human ear performance, then you can now get the electronics, the op amps and the microphones and the speakers and so on to put together the hearing aid, and hopefully it will behave exactly how the model said it should. Yeah? I'm not too sure why this is showing so blurry. Are you all seeing this clearly, or are you seeing this blurry by any chance?
So it's a little blurry, but you can make it out.
Yeah, I'm not too sure what is happening here. Hold on. Oh, okay. Just now, let me. The next one seems to be all right. Okay, this one, the blurry one, and you all have it online. Actually, yeah, the system is not dealing with the inputs correctly. Exactly. Very good. So at least somebody is paying attention, and that is exactly what's happening. So I'm putting something, and you can imagine how complicated this particular system is, right? And the amount of processing that has to go on. So we in our case, the language of our models is mathematics. So like it or not, and you all have done a lot of mathematics in school and you've been doing math here, math is the shorthand for electrical engineering, and it's a shorthand for all of our models. So instead of describing a current by drawing a waveform on a screen, right, on a piece of paper, I could describe the equation, the current or the voltage by writing an equation. So in this particular case, IT is 30 cosine 40t minus 20. And by now you should be able to know, well, if you were to be asked, well, what's the frequency of this current? You could pick it out because the frequency is in this somewhere inside of here. You will get the frequency information. And from that, you can determine certain other parameters. So for instance, what does that 20 tell me? Anybody remember what the 20 would signify? Right, I have three answers here. The correct one, it was the third, which was the phase shift. Right? Now phase, we'll talk about that as well. Phase just has to do with a delay in time. So this is just simply telling us that the 20 means that instead of the current being 0 at time 0, at some phi 20 radians away from 0 is when the current is actually 0. Right? So it's shifted around in time a bit. That's all it's telling us. But that is very important, and that is one of the things that severely limits how systems perform. Right, so it's very important, and I'm good at least good to see that at least some people remembered what phase was about. So let's get this out of the way, this blurry one. And I just have a little question here. If your wall frequency, your wall voltage is 120 volts RMS coming out, depending on where you are in the system, in the where you are in the region, you can write out what the voltage supply for your residential voltage is. Some countries have 60 hertz, like Trinidad. I believe Barbados has 50. So depending on where you are, this part here would change a little bit. Yeah, but you could try that. Or just at least you need to know what your own particular situation is. We are 60 hertz here. So back to clear slides again. So the relationship, of course, and then there's a relationship between the what we draw, which are the visual aids, the diagrams and so on, and the mathematics. So again, from last year and even maybe at CAPE and so on, you would know how to draw a schematic diagram, right? So this the schematic here, the normal schematic symbols. But this now, there's an equation that describes the AC operation of that. And we call that, of course, a differential equation. So you can look at this diagram, or you could describe the diagram in this particular form. Both tells you the same thing. This is a series RLC circuit, and this is the piece of mathematics that describes the behavior of that series RLC circuit. So what this is, now just think about it. If you were given a circuit in a lab, for instance, and you have to go and now somebody asks you, well, you know, I have a signal generator here that, let me just get a different color. What color we have here? Yeah. I have a signal generator. Oops, I don't know what I'm doing here. Right? I have a signal generator here, and let's get rid of that. I have a signal generator XT, and the signal generator now is giving me some, I could get, let's say, 5 to 15 volts, and the frequency, okay, 100 hertz. And I want to see what YT does as I vary the resistance, right? So I have a variable resistance, and I want to see what YT does as I vary it. Of course, you could sit down there, you could wire up the circuit, you could get a whole bunch of resistors, and you put it down on your breadboard, you put the signal generator on, you set it to a particular value voltage, you put the resistor in, and then you measure the voltage YT, which is the voltage across the capacitor. And then you go and you change the resistor, and you change it, and you go on. Or if you have the description that we have here, right, which is the differential equation, what you can do now is to just simply solve that equation, and then you will have the behavior of YT in terms of X. So I can vary X to my heart's desire. I could put in R and L and C, whatever values I want, and I could just simply see what the answer is by plugging in the variables. And that's the beauty of the model. So once I have the model here, if I wanted it to do behave in a particular way, right? If I wanted the model, well, just now. So, stop behaving here. Let's trash that. Good. Yeah, if I wanted the model, if I wanted the circuit to behave in a particular way, all I have to do now is to plug the values into the model, and then once I'm satisfied, then I go ahead and get the and then get the components and put it down on the breadboard, and hopefully it will work the way I wanted it to work. And then, of course, last semester, you spent some time learning something called a Laplace transform. Again, this slide is crunching up a little bit here. But if you take that equation that we have up, the differential equation that I have up there, if you take that and you find the Laplace transform of that, then you get something else. And that particular relationship now allows you to manipulate behavior in a slightly different way. So for instance, instead of trying to solve that differential equation by longhand, and there are ways of doing that, you have to integrate it, and you have to find integrating factors and the like, you can use another tool that a mathematical tool that we would taught, which is the Laplace transform, that will allow you to solve that equation. And again, once you solve the equation, you can now plug in the variables, and you see how the particular system varies. And then if it works well, then you go back and you breadboard the thing, right? And we'll talk a lot more about that as we go through. Another visual representation that we use a lot of here and in controls is something called a block diagram representation. This is just an arbitrary representation of the inside of some imaginary system. But each of these boxes, the G1, the H1, the G2, and the H2 in there, each of those things represents a model for a particular element. It could be a motor, it could be a valve, it could be an electronic amplifier, and so on. but we treat them in these big blocks here. They're all interconnected. So using techniques that we will learn, we can just go through this entire thing here and simplify it. And then once we've simplified it and we understand how it works, then we put the inputs in, we get the outputs. If it behaves how we want, then we go on and you start to build it. Yeah? Everybody clear on the idea of modeling? Any questions?
No question so far, sir.
Very good. Okay, we have a spokesperson. Right? As I said, sometimes I'll say if you put your hand up, I will see it come across the screen, but not every time I'll be able to stop. Okay? But again, if at any time you are not following what is being said, or you want clarification, or you have another view of what is being said, feel free to stop and let's discuss it. Okay? So we have the block diagram, right? So let's talk a little bit about signals. So we will, all of those things we're going to expand on going forward. Signals for our purposes come in two categories, two flavors if you like: continuous time and discrete time. The continuous time, both of them are functions of time. The thing about the continuous time is that it has a value, it has some magnitude for all values of time. So it exists for all time. Yeah. And a good example of that, for instance, on audio waveform, or the voltage coming out of the wall socket, for instance. If you put put an oscilloscope on it, what you're going to see is a waveform that is continuous, right? There are no breaks in it. And if you look at it at all points in time, I'm not going to have to do something about my pointer. I can't get a pointer. But if you look at that sinusoid, that kind of crunchy sinusoid in the middle there, all points of the sinusoid have a value. All points of that signal have a value. Okay? Most of the signals in the physical world are continuous time signals. So voltages, currents, pressure, temperature, velocity. If you're working in process plants and they're measuring temperatures and flows and pressures and the like, they're all continuous time signals. In other words, once the plant is operating, that signal, the voltage or current or the pressure or temperature and so on, there is a value being produced all the time. There are no gaps. Yeah. The other side, now this is yes, now. Yeah, this is getting blurry again, but I'm not too sure why. Let's see what else we have here. Okay, anyway, let me put up something. So for instance, if I were to take, where's my whiteboard? Excuse me a second here. Let me see. Right, there we go. Right, you should be seeing a whiteboard in front of you, yeah? Right, good. So I've drawn something looking like a bit of a sine wave there. If instead of that, I am only able to see that particular sine wave at particular points in time, what I'm going to see is something looking like that. Okay? The values only exist at those points, nothing in between. So in between here, for instance, or here, I have no idea what that particular signal is doing. I know what it is here, I know what it is here, I know what it is here, but nothing in between. This is what we call a discrete time signal. Oh, let me write this a little bit. DT. I'm writing this with my finger on a touch screen, right? I missed my whiteboard, but anyway. So this is what we call a discrete time signal. It only exists at those particular points in time. And it is what will happen if I could only observe the continuous time signal at certain points. It's like taking a picture. So something is happening around the place, and you snap a picture with your with a camera. At that point in time, that is all you could see at that point in time. You know what went on before, you don't know what went on after. If you take a picture 2 seconds again, you will see a change from the previous one, but you have no information as to what went on between those two values. This is what a discrete time signal is. Yeah? So let me go back to this slide here. And see if we are clear, a little bit clearer here. Right, so we're back to the blue slide here. So this sinusoid here that you're seeing, those circles, the dots actually, are only, that is all you know. And we call that a discrete time signal. What's the purpose of a discrete time? Well, we'll get to that in a little while. Okay, there are certain things, and here's where the examples come in. There are certain things that exist naturally as discrete time signals, right? In biology, for instance, the position of the bases in your DNA. That is a discrete positional signal. It exists in a particular position and nothing else. Or, for instance, when certain things multiply. And again, we have this thing like with the coronavirus and so on, when viruses multiply. You know, one splits to two, splits to four, and so you keep going on along the road. If you go down in between, you will never get with a binary split. You wouldn't get something happening every 3 occurrences and so on. It happens at discrete intervals at multiples of 2. And in our case, for instance, we have a lot of man-made discrete time signals. For instance, the stock market quotes, they quote it at particular times of the day. Digital images, what you take with your cell phone and so on, those are discrete time, what do you call it, signals, right? Video files, when you're sharing video files or you're streaming movies and so on, those are discrete time files that you have here, or the daily statistics that we get on the COVID situation here, right? Yes, Akim. I see your hand is up. Question? Okay, not working. Okay. But what's the question? Perhaps you could just type it quickly. Right. Right. No, the MP4, all of those, and we'll talk about that all the way. No, the MP4 file, everything what you're watching as an MP4 file is really data. When they were making the particular video recording, they were actually sampling the pictures at an extremely high rate. And it's compressed, it's modified, and it's what do you call it, coded and sent to you. So when you are seeing it, your eye and the computer interprets the thing as though it's continuing all the time, but it actually is not. There are successive, very very rapid succession of yeah, there you go. Somebody's putting the that's the audio frequency, the 44 kilohertz sampling, right? But it's actually sampling at a particular number of frames per second, or in the case of audio signals, you're sampling high fidelity audio is sampled at like 44,000 hertz, 44 kilohertz. So although it sounds continuous, it's actually being processed at 44,000 times a second, and that data is coming towards you. So it's all discrete, yeah. And we'll talk much more about that as we go along. Right, 60 frames. Look, right. So somebody's pointing out that 60 frames per second. Your eye interprets that continuously. But if you were to, for instance, I don't know if you ever tried sometimes to take use your camera and take a video of your screen. You start to see some lines appearing in the screen and so on. That's because both the screen is sort of flickering at 60 frames per second, and the camera sometimes tries to record that at the same taking it in fluorescent light. The camera is trying to record that at the same 60 frames per second, and what you end up seeing is a flicker. All right. So yes, there are a lot of tricks where we continue the no, it's the other way around. That question. Let me just see that last question there. Somebody put up one. Hold on. Somebody put up. Are continuous signals just discontinuous signals with a high sample rate? Just as is the other way around. That are not discontinuous. That the discrete time signals are continuous signals with a sample rate, and we'll get to that in a second. All right? Akim, your hand is still up, or I could take it down. All right. Great. So, okay. So maybe to further clarify something that was asked before, why discrete time signals? Well, first off, discrete time signals, we can do some processing with computing power, with microprocessors or microcomputers or digital signal processing systems. Electronics can handle discrete time signals and can do a whole number of things with them. And again, the fact that we are being able to interact now is because of discrete time signals. The fact that the slide on the screen is messed up is because the discrete time signal is giving me some issues here. And the software and however Blackboard is trying to reassemble the slides is not working as well as it should. All right. So one good thing for us to remember, and this is at least on the handouts that you have is very clear. For us, a continuous time signal, it takes a continuous time system takes a continuous time signal coming in, and it gives me a continuous time signal going out. A discrete time signal has to take a discrete time system has to take a discrete signal coming in, and it will give me a discrete time signal coming out. And the discrete time signal is just a set of values. Okay, that's the beauty about it. And and we're going to discuss this a little bit later on, but from an electronics perspective, how do we obtain a discrete time signal from a continuous time? We do that by a process called sampling. And sampling conceptually is exactly like what you're seeing here. You have a signal coming in, xt, right? So you have the signal coming in, xt. You have a switch, and you have the sampled signal coming out. The key to all of that is this capacitor here. So what's going to happen is that my signal comes in, and let me just maybe put up that whiteboard again. Where am I? Right. Okay, you could get past that. Right. So here I have, if I have that sinusoid coming in inside of here, I can know if I pass it through. So I have the thing, I have a switch, I have a capacitor, and this is the output here, right? So the capacitor is here, right? Eventually I'll get a stylus, so I'll get these drawings a little bit better as we go along. Once the signal comes in here, so the signal is going in at this point here. Once the signal is going in, if the switch is open, the capacitor has nothing stored in it. Once the switch is closed, at that point in time, the capacitor is going to go up to the to whatever is the value of the signal at that point in time. So the capacitor is going to store, is going to go from 0 up to some particular value, right? I open the switch, the capacitor is going to hold that value for a little while. If it's a good capacitor of no load, no resistance on it, the capacitor is going to hold that voltage for some time. I close the switch again, and now whatever the voltage value coming in, the capacitor voltage is going to go up to that and hold that value, and I open the switch. So it's going to hold that value now until the next time I close the switch, and then the capacitor is going to charge or discharge to whatever the voltage is. Then I open the switch, close the switch again, the capacitor charges or discharges to whatever the voltage is at that point. Open the switch, it holds it, close the switch, open the switch, close the switch, open the switch, and so you go on. So what you end up getting are these series of values here, yeah, that you use. The capacitor, no, the capacitor doesn't create the interval. You're switching. How fast you open and close this switch creates that interval. The capacitor is going to hold a value between the intervals, right? But how fast that interval is dependent solely on you opening and closing that switch. All right, so let's go back to this slide here. Try and get back the slide where we were. Right, and all of a sudden it's showing clear again. So that however rapid you open and close this particular switch, that is what determines how fast you sample. And as somebody was saying, like the frames per second for a video image, if you're taking 44,000 images per second, it means that sampler switch is opening and closing 44,000 times a second, and whatever is storing the value is going to be charging and discharging at 44,000 times a second. All right, so conceptually it's like that. The switch, of course, because we're all dealing with electronics, it's very easy to make an electronic switch, and we'll, you know that from your work before, something like a field effect transistor or normal BJT, right? You bias it and it conducts. You remove the bias, and it's an open circuit. Especially a field effect transistor, it's very easy to have it work as a switch. All right, and internally to a lot of electronics now, you don't have to have a mechanical switch. It's actually something that is done electronically. Now, sampling itself is a whole process, and we'll talk more about it when we're doing the Fourier, the section on the Fourier transform. We'll talk a bit about it, and it's at the core of another course that we have, which is discrete time signal processing, and it's very important in terms of whether the discrete time signal represents the continuous time signal accurately or not, right? And again, just think about it. If I have the sinusoid here, if I were to just sample it here, here, and here, those three points. So here, here, and here. All you would have, if anybody was to show you anything, you have this piece of, you'll have these 3 bits of data if you plot it out. 3 points here. Does that look anything like a sinusoid? No, you have no idea what happens between those points, right? So you have no idea what was sampled before. Okay, so clearly, depending, if I were to sample it faster and I had the values here, 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 and so on. Now you can start to get it will fill in the blanks a little bit. And slowly now it's starting to look something like a sinusoid. So again, just conceptually, the faster you sample, the better the representation of the real signal is going to be. And that, but it's not a random thing. Like in most things that we will do, there's for want of a better word, a formula for doing it. There's a correct way to do it to avoid the situations where you take the signal, you sample it, and then what you have are these 3 points here that are totally meaningless. All right. So let's see. This was again just to sort of get us thinking along what we are about. We are dealing with 3 things. We're dealing with signals here. The signals could be continuous or it could be discrete. We're dealing with systems. The systems can be continuous and discrete. And we model the systems using some shorthand. The shorthand for us may be mathematics, like discrete, like differential equations. It may be other types of mathematics, like the Laplace transform, or it may be diagrams, like the block diagram that I showed. And all of those things we will meet and we will spend some time and discuss as we go along. Yeah? So questions? Questions and concerns? Not officially. Somebody is asking if we will use Simulink. Maybe later on as we go through and we're doing the block diagrams and this block diagram simplification, we will use Simulink. You have access to MATLAB and Simulink, and of course nothing stops you from playing around. I like that. I mean, if people were to experiment and in between you're using MATLAB or you're using Simulink for something, and you come across something interesting, right? Or something that looks confusing, and you want to discuss it, bring it to our attention, and we will take it up there. Simulink and MATLAB are the modeling environments, 2 other modeling environments that we use. So again, like for control systems, which you will meet next semester, they model the controls using the symbols in Simulink, or you can model it with lines of code in MATLAB. MATLAB and both MATLAB and Simulink are very friendly, right? If there are mistakes, it prompts you very, very quickly that this doesn't make sense. So it's very hard to put in a false behavior or something in there and get a crazy answer coming out. It will try to prevent that always. But it's really good, and I will use it here, especially when we get into talking about the Fourier transform or some of the other things as well. We will touch on MATLAB, and if possible, I'll use Simulink as well. And remember, there are other tools as well that are available. If you don't have access to MATLAB or Simulink, there are what do you call it? Free version, not free, but open source versions like Scilab, for instance, or Octave, that work with virtually the same command structure word for word that MATLAB uses, but it's free. Right, so if you're having difficulty with the MATLAB license and so on, or downloading it from where you are, you could try those as well. Right, so there are all sorts of tools available. You have the Wolfram Alpha, and you have Symbolab and so on. There are lots of stuff available now. Okay, so we will use as many of those as possible. Because officially we use MATLAB, and because MATLAB is used elsewhere in the program and maybe in your courses and so on, MATLAB will be the one that I will tend to focus on if we are using it, but it's not absolutely necessary. All right. So any other questions? It's up to you. Somebody was asking to go through the video links from today. If you have time, just browse it through. I mean, the beauty about the video links and so on is that they are there. So it's for you to look at. Some of the links that I've put up have been there to help people for like convolution, with convolution and some other concepts and so on. It's not necessary at this point in time, but you could go. That's why I put it up there. So you could have a look at it and start getting your mind around the things that we will be discussing. All right. It's not as complicated as it looks like, but you have to sort of pay attention and clarify things early on. But feel free and explore. I mean, that's what you're engineers. So you're not in class. You're just to listen to me, right? And I don't know how many of you all actually going to buy anything called a book any longer. So the information is outside available. Use it. Yeah. And if something doesn't make sense or something, one of the things you will notice is that certain either lectures or books or texts or resources and so on, sometimes the symbols that they use may vary. All right. And the Laplace transform is not so critical in that regard. But later on, in the middle of the course, when we're talking about the frequency responsive systems and we're doing the Fourier series and Fourier transforms, you may notice that the symbology that they use varies from time to time. Okay, so if it's looking too different, I would suggest that you kind of stick to what we do and avoid, because what you wouldn't want to do is to do something where the symbols are different than what we're doing, and then you end up getting the wrong answer. Okay. But that's just because people from different backgrounds and authors from different parts of the world sometimes use different symbols to mean the same thing. Okay. So any other questions? Okay. So if that is the case, I will stop the recording.